You guys being silly over there again? Silly giggles. Yep, that's for yes. Silly giggles. So when we left off yesterday, we were trying to muscle through the fourth example. I don't think the last examples today will take as long. Yesterday is always the hardest lesson because we're not familiar with like how all this stuff works. So this will be, generally speaking, the hardest of all the examples, just for the record, and then I think it's downhill from here. So today is the 7th. And this is just a continuation of yesterday's notes from the 6th. So we had stopped at a point where we had an equation. I'm assuming you were here yesterday, so we would just literally resume the notes just right off of as if it were still yesterday. So we had an equation that had said 13,000. Remember, that was our final amount in the account. $300 was our principal investment. And then we had 1 plus. The interest rate was 5.0%. So we had, of course, written 0.0507. You never ever want to lose points for not moving the decimal correctly 2 places to the left. That seems kind of silly. So, and then it was daily compounding, and we used 365.25. Remember, you got to throw in the 0.25 over extended periods of time to account for the leap years. And then our exponent n times t was 365.25 times t. And so we pick it up from here. The what makes this a unique situation, and I'll still be talking about this in a week, is the fact that the variable that we're trying to solve for is not anywhere where we can play with it right now. It's another nanny nanny boo boo guy. That t is up there just mocking you from up in the tree branches. And little does the t know that we actually have a way to bring him down. And so we learned a week or two ago, or 3, that you can bring powers down if you use logarithms. And so the idea here is the first thing we have to do, for those of you like staring around the room and daydreaming, you should stop that. The first thing we have to do is get the power by itself. And this thing right here in the yellow box is called the power. Anything that has a base and an exponent together, we call that a power. And so step 1, without negotiation, is we have to divide both sides by 300. So you probably want to put it into a calculator and see what kind of results you get. If it doesn't come out nicely, then we're going to want to just leave it as a fraction. We don't want to taint it. And I'm not a huge fan of that as a decimal. So what I'm going to do is just do a little bit of grade school work here. So if I think of 13,000 divided by 300, again, I don't want to put in 43.3. That's disrespecting that number. So we want to keep it pure. Yesterday, we had an example that came out to 68. So we were like, yeah, let's just put 68. We don't want to mess with the decimal here, not this early in the stage. So basic reducing of fractions says that I can cancel out a pair of zeros and then another pair of zeros, which tells me then what I want on the left side, so that I don't want anything inexact. I have 130 over 3. So that, again, is just simple reducing. That's just literally dividing the top and the bottom both by 100. And then that leads us to just the other stuff. So plus 0.0507 divided by 365.25, all to the power of 365.25 times t. So this is where you make the power play. And again, if you don't have this power play in your back pocket, then you never have this card to play. And it's a shame. You go through a lot of math and you're hamstrung, your hands are tied. And if you know how to pull something down out of an exponent, you're massively more powerful than the person sitting next to you if they don't. So what we're going to do is we're going to apply a logarithm to both sides. And in the same way that we can drop logs off of both sides, you can, of course, apply a log to both sides. So free of charge, I'm going to take on the left-hand side and rewrite the left-hand side as the log of 130 divided by 3. I'll say it again. If you can drop a log off of both sides, then you are allowed also to bring a log into both sides. Take the log of both sides. Now, when I do this right-hand side, I'm going to leave a little bit of space here. And some of you might already know why I'm doing this, but so as you know, once you have a log applied to both sides, you are totally within your rights to take the exponent of the argument of the log and move it down in front of the log. That's, as I said a long time ago when we first learned this, there would come a day when we would really appreciate the beautiful power of that property. And today is that day where you really get to say, okay, this is like a whole new world of mathematics that I can work with because I know how to do this. So what we're going to do, because we have logged both sides, is we're going to take the exponent, this little fellow up here, and we're going to pop him down into the front. I didn't quite leave myself enough space to make it perfect, but by doing that now, we've brought the variable now down onto a level playing field with everybody else. You can't work with him when he's hiding from you and cowering up in the tree. But at this point now, I would encourage you to view this through the correct set of lenses. What we have here, I'm going to underline one thing, and well, I'm actually going to put a box around it. I have a red boxed number times the letter T times a blue boxed number. And I don't really want to move on until I'm sure that you agree with me that what's in the red box is just a number and that what's in the blue box is just a number. Can we agree on that? Then by that logic, at this point in time, if I said to you, just basic algebra question now, how do we get T by itself? What would you say? Keep going. You could do it in 2 steps if you want to. I'm going to start with what Bryn said. I don't know if you heard her or not. We can divide both sides by 365.25. That'll at least get us closer to the promised land, right? But then we're going to have to turn around and divide again. And if you're more comfortable doing this in 2 steps, that's okay. I hope you agree that if we divide by the red box, we're closer, but then we go, oh, now I have to divide by the blue box to finish the job. But algebra never changes. I mean, if you give me a variable and stick it between 2 guys multiplying by him and tell me to get it by itself, 100% of the time, I'm just going to divide by those 2 idiots that are stuck to my variable, right? So you can do it all in 1 step at this point in time, or you can take your time and do it in 2 steps. So let's do it in 2 steps and see if that maybe eases the calculator burden a little bit. So the first thing you're going to want to do right now is grab your calculator and type in log of, and then it's going to open parentheses for you. And notice when I applied a log, I just applied a generic common log with a base of 10, right? Because that's what your calculator is going to be most happy with. You could have used a log base 4, but like, why would you do that? Right? That's just weird. Could have done a natural log if you wanted to. Doesn't matter. So I'm going to type in log. It's going to open parentheses. I'm going to type in 130 divided by 3. I'm going to make sure I close those parentheses. That's really important. That ends the log. And then I'm going to hit another divided by, and then I'm going to do 365.25. And if at this point you'd like to, hit enter, and I'll get caught up to you so that we can all agree on the answers at this juncture. You should not care at all about the number that's on your screen. I will tell you though, at this point, if you've done it correctly, your screen should say 0.0044813747. Is that a match? 0.0044813747. Yeah, I may have a longer screen than you. I'm using my TI-84. So on your TI-30, you might not see all those places. But I mean, if it starts with 0.004481, then you're in great shape. So we agree? Mm-hmm. Don't write that number down. All that's going to happen if you write that number down is A, you're going to annoy yourself, and B, inevitably, you're going to round it and lose accuracy. You can't see it right now, but there are a lot of decimal places stored in your calculator's memory. I don't know how far they go. I've never researched that, but I guarantee it's more than we can see. So leave it pure. Now, with that number sitting on your screen, again, let's talk basic algebra. What do we have to do after this to finish the job? Divide by the blue box. And so at this point, with that sitting on your screen, the good thing about modern calculators is you don't have to type it in again. If you just right now with that on your screen, hit divided by, and if you're using any form of decent calculator, it should say like ANS or something like that. What that means is it's saying, oh, so you want me to divide the previous answer that I got by what you're about to give me. Got it? So it says ANS and it says divided by. Now let's all type in. So your screen looks like this. Mine looks like this. ANS divided by. That's answer divided by. And then I'm going to type in log. And then in parentheses, I'm going to just do what's in the blue box, right? Just log of 1 plus 0.0507 divided by 365.25. Make sure you close those parentheses and hit enter. This number you should care about because at this point, the algebra is done. You officially now have t by itself, and you should have come up with t. And we'd want to probably use the squiggly equals for most of these answers, you know, because you don't have to put equal signs at all. Like you could just put the answer. But in my case, if I say t equals, I'm going to say t is pretty much equals, and I'm going to say about 74.34 years. And that might seem like a long time to you, well, because it is, but it's a reasonable expectation. If you go back and look at the original problem, turning $300 into $13,000 with such a paltry interest rate, that takes a lot of time, right? That's not a lot of nest egg to start with. And then 5% isn't going to do a lot of damage very quickly. So any questions on that? Okay, so that leads us then to the second half of these notes, and I'm hoping that this will go quicker. I wish I didn't have to do all this, but I'm sorry in advance. It's just I don't want to leave stones unturned and then have to go back and plug all the holes. So what we have to get to now for the last half of this, and I hope these go quicker, is something called continuous compounding. And I don't know if it's going to be tomorrow. If I had to guess right now, it'll be next week. I did find a good YouTube video. I've been kind of holding it in the queue that I want to show you that will finally make sense and explain where the number E comes from, like who discovered it, how does it come to be what it is. But E will be involved in this. The way continuous compounding works, think about this, is if interest can compound daily, couldn't it compound every hour? Couldn't it compound every minute? Couldn't it compound every second? Could it compound every 100th of a second? Yeah. Math doesn't care. The interest will compound itself as frequently as someone tells it to. So theoretically, if interest just keeps compounding faster and faster and faster and faster and faster, you reach a point where the number of compoundings becomes infinity. It's literally compounding infinitely many times per year. And this formula that we've been using is no longer practical. You can't put infinity in place of n. It doesn't make any mathematical sense. For that reason, we have a new formula. And again, I hope this formula makes more sense like a week from today. Today, it's just going to be a formula. It's going to be a thing that my teacher told me I have to write down. So here it is. I call this the PERT. You should like this formula better. I mean, it's nicer, it's neater, there's less clutter. It's only got 4 variables instead of 5 because E is not a variable, right? So N is the guy that has now stepped out of the way because again, N is infinity and E replaces that entire concept. And so this formula, the variables, I don't feel like I need to go through this with you again. A is still who he was yesterday. P is still investment amount. R is still the interest rate as a decimal, and T is still the number of years. And again, E is a number, not a letter. So having said that, let's do our first continuous compounding problem. And I don't think you're going to, bless you, I don't think you're going to encounter much stress with this. So how much would you have in an account if you invested, bless you, $4,000 compounded? Did I spell that? That looks weird. Compounded continuously. At 7.5%. So our cast of characters was going to be shorter this time since there's only 4 variables. We're only going to list 3, and then of course we'll solve for the 4th. So as I make my cast of characters off to the side, who's A? Who's A?
No.
We don't know. So A is a question mark, meaning that when I fill in my formula, I'll just replace it with A. What is P? What is R? You should always write down R as your decimal point. 0.075, right? Just get used to always saying that as a decimal. And what is T? Good. You should feel absolutely no stress here in the next like 2 minutes when this problem's over. I know yesterday, I saw people looking around like, what just happened? This one, you shouldn't feel that way. This is like light work. I got this now. The worst is over. So when I go to plug this in, I'm going to show my work, and I'm simply going to write A equals, here we go. I'm going to write 4,000 times E. And then for my exponent, I'm going to go ahead and multiply out R and T. Remember, your exponent is a multiplication problem. Today, instead of NT, it's RT. And so I'm going to do 0.075, and I'm actually going to multiply it by 45, and I'm going to get 3.375. And what's nice about finding A problems is you don't have to do any work beyond this. Come quiz day, this will be what I mean by showing your work. If you don't show this, I probably just won't grade it. But that to me is the work, because now there's no dividing both sides or rooting or logging or anything like that. It's like done. I just got to type it in. So let's all give it a shot. The way you're going to do it on your calculator is you're going to first type in. I'm just trying to show you what your screen would look like. I'll use a TI 30. Mine looks like most of yours. So first I'm going to type 4,000. Above the natural log button, it's the 3rd button down on the left above ln, you should see e to the x. So now you'll want to hit the 2nd button, the blue button, and then hit the ln button, and your screen should now look like this. So we're doing 4,000 times e to the power, and it's just waiting for the power. And in this case, you could type in 0.075 times 45, or you could type in the result of that, which we've already done. So I'm just going to put in 3.375. I'm going to close those parentheses. I'm going to hit enter. And I'm going to figure out that the answer is going to be $116,897 with 14 cents. And I rounded the 3 up to a 4 because there was a 5 after it. Any stress about that? Okay. To save time, would you guys mind if I stopped writing these as word problems and just gave you the meat and potatoes part of it? Is that okay with you? Just to save some time in the notes. So, you know, there would be a paragraph about blah, 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 blah. But at the end of the day, what really matters is that we want to pop out the pertinent information. That's always what my red list of characters is on the left. So let's jump right to that step so we can get some work time here today. So this time, let's say that we have an account whose final amount is going to be $432,000. The principal is what we will not know. I'm going to do this in the same order as I did it yesterday. Let's say that the interest rate is 4.16%. So let's do 0.0416. And for time, let's say that the money sat there for 50 years. So if this were in paragraph form, it would say something like, how much would you have to invest in an account that compounds continuously at a rate of 4.16% for 50 years for the account to be worth $432,000? It would say that, something like that. Good. All right, let's get to it. So step one, just like yesterday, my expectation is that we will start by writing the PERT formula. And I know to use the PERT formula because of the word continuous. So that's not really written over here, but if you're sitting in class or watching the video, you already know, of course, that today's entire lesson is about continuous compounding. So that would have already been stated. All right, let's do this. What are we going to put in place of A? What are we going to put in place of P? What are we going to put in place of E? E, good. And what are we going to put in place of RT? Is that what it comes out to? Thank you. So 2.08. Do you guys have any questions so far? Okay. So again, the algebra to me seems basic. If I said to you get P by itself, you ought to just instinctively look at it and say, I can do that. How do I get rid of the thing, that parasite that's stuck to my P? How can I get rid of the P or get the P by itself? Just divide, right? So what we're going to wind up typing into our calculator is 432,000, no commas, right? Divided by, so I'm going to type it, oh, again, I'll use the same calculator as most of you. 432,000 divided by, and then again, hit second natural log, and your screen should look like this, and it'll have a parenthesis, and then you're just going to put in your 2.08. Oops, I forgot the 8. And we figure out that you would have to have made an initial investment of $53,969 with 85 cents. Did we all get that same answer? Yeah. Wonderful. Questions there? So again, let's cut right to it. Let's bypass the copying down of the long paragraph question, and let's just get right to the meat and potatoes part of this. Now let's make our cast of characters. Again, this is a continuous compounding, of course. And so this time, let's say that we know that the final value of the account is $94,000. We know that the principal or initial investment was $4,800. The interest rate is what we don't know, and let's say that the time is 34 years. Good, good. All right, what's step one? Write that formula, write that equation, you bet. So we're going to start by writing out the equation. A equals PERT, and remember it's P times E, and then both the R and the T are up in the exponent multiplied by each other. In place of A, we're going to put 94 grand. In place of P, we're going to put 4,800. In place of E, we're going to put E. And what's my exponent going to say today, this time? 34R, very good. So this is another one like the last example from yesterday where I can't just put a number up there, right? If one of the things up there I don't know, then I can't just put a number. So this should look familiar. This is how we started class about 15 minutes ago, 20 minutes ago. What's the issue? Like what red flag? Because you got to always have that red flag. People that are good at math have their red flags. They see something and it makes them do something. What catches your eye? Variables in the exponent, right? When your variables nanny boo-booing you from up in the tree, you got to go, okay, I got to bust out a different set of weapons here. So we know we're going down the log path here. What do we have to do before we can apply a log? Divide by 4,800. So let's take that for a test drive and let's just see how it winds up. I would always prefer to put an actual number there instead of some annoying fraction, but sometimes you just get what you get. So once again, it's going to be a fraction. And so I don't want, or a decimal, I don't want to go down that road. So if I cancel out the zeros, well, here's what the number would look like. It would be 940 over 48. But we can even go a little smaller than that if you want to. Reducing here really doesn't matter because it's like we're going to use a calculator anyways. So we can just leave it as 940 over 48. Genius. So I'm going to just leave it as 940 over 48. You could reduce it all the way down if you wanted to. You could divide them both by 4 or something else. But again, there's no real benefit because the calculator is going to do all the heavy lifting anyways. Equals e to the 34r. What do we do now? How are we going to get Mr. 34r to come down and play fair? We're going to use a log. However, since there's an e involved, methinks that we should natural log both sides. So I'm going to do the natural log of both sides. And why would I do that? You'll see in just a moment, because we're going to get a redundant log. Trust me on this one. Don't use a log base 10. I mean, it does, you can still do it. It's just slightly more annoying if you don't choose wisely. And by using a natural log or any log, I have now brought into play this game where I can grab my exponent and say, zoop. You are now down on the level playing field with everyone else. You're not so funny anymore. Let me ask you a question. What is the natural log of e? It is 1. Meaning that in this case, I can actually just completely get rid of that bad boy. And that, to me, is worth it. Natural log of e, I'll take that. Anytime you see a problem with a 10, you should use a log base 10. I mean, generally, you'll always use a log base 10. Unless there's an e. If it's a PERT formula, you should natural log. And then, of course, this is, I hope, an easy algebra question. What's the last thing we have to do to get r by itself? Just divide by 34. So into our calculators, we are going to let the calculator, as I said, do all the lifting for us. We're going to type in natural log, and then it's going to open a set of parentheses for us, just like this. We're going to type in 940 divided by 48, and for the love of God, we're going to shut those parentheses off. If I had $1 for every time a kid was like, what did I do? And forgot to close parentheses, I could probably retire. So we have natural log of that, and then we just hit divided by 34. And we should have gotten this. I'm going to copy what's on my calculator screen so that you and I can talk about what to do next. And so my calculator screen says 0.087490555. And you may not have all those digits, but you've got at least like 6 or 7 of them. So because this is an interest rate, I now know instinctively that I have to move my decimal 2 places back to the right. And so I scooch first. Do not round and then scooch. Scooch, then round. So at this point in time, my answer is going to be 8 point. Now, this is where the 2 decimal place mark will be. That white wall indicates the 2nd decimal place. It's not the 4th place anymore because I moved them twice. So it's going to be 8.75%. Still good? Roy, yeah, Jared.
What is stopping us
from whatting?
So when you use the natural log with the e,
right?
You said the same thing happens with
tens. Yeah. So like if you ever saw a problem where we're working with a 10, like instead of an e, which is pretty uncommon, quite frankly. But if you had a situation where you had like 42 equals oh, excuse me, I didn't mean to do that. If you had like 42 equals like 10 to the 13 teeth or something like that. You see that in this case, the benefit of using a natural log would not exist. But if I logged both sides, then I'd have log base 10 of 42 equals 13t times log base 10 of 10. Can you see that? And then do you see also the redundancy in this case that log of 10 is going to go poof just like natural log of e did? I say generally, I think 9 times out of 10, when you don't have any other reason to, you'll just use a log log. But when you see the E, you should think natural log because it saves you that little bit of annoying work that you have to do at the end, right? It's not a big deal. Last one, let's make this official. Any good compound interest lesson involves 8 examples, and I'll show you what I mean to give it some closure here after this example. So the last thing that we have to talk about is a situation, again, that's continuous compounding, and the cast of characters this time will be, let's say you have an account, and at the end of its maturity, it has $1 million in it, and you started with a paltry investment of $15,000. All right, so maybe like on your 18th birthday, you get an inheritance, and instead of blowing it on some stupid car, you're like, I'm going to invest this. And then you go back on your, whatever, 68th birthday or something. I don't know what it is. And let's say that the interest rate this time is going to be given, let's say that it's 7.165%. The question then, of course, is how long would it take? And this may not be realistically within a human lifetime, but I guess we're about to find out. So got the situation. There it is. We're looking for how long it takes. This will complete the cycle of solving for every variable under every scenario. So step 1 is write the formula. And the formula is final amount equals PERT. P times E to the RT. In place of A, I'm going to put $1 million. That's a 1 with 6 zeros after it. And then in place of P, I'm going to put 15,000. In place of E, I'm going to put E. And then what's my exponent going to be? Yeah, it's going to be 0.07165 times T. Don't skimp on decimal places. The only time you should ever skimp on decimal places is at the very end, when everything's done. Then you can round as necessary. So what's step 1? Right, does it come out nice? Has anyone done it yet? Got another decimal. So let's just knock off a bunch of zeros and just, again, it's not a big deal. Since the calculator's doing all the work, like, why do we care, right? A shorter decimal or a shorter fraction is only going to make less buttons we have to push. So I would just always take the freebies, knock off the courtesy zeros. So if I take 3 zeros off of $1 million and 3 zeros off of 15 grand, my number on the left is a nice little pretty 1,000 over 15. And that's good enough for me. You could go further, but again, there's no benefit to that. So 1,015ths equals E to the power of 0.07165 to the power of T. And of course, you know by now, since the T is nanny boo-booing us from 13 feet up in the tree, what are we going to do? We're going to log both sides. More specifically, we're going to natural log because we see that there's a benefit to that. So on the left-hand side, I'm going to have the natural log of 1,015ths. And on the right side, I'm just going to have 0.07165 times T. Look at me skipping steps. Don't yell at me. But you know that if we natural logged the right side, where this would have gone, we would have brought down the exponent and it would have been multiplied by the natural log of E, which would have just gone poof, bye-bye anyways. So we arrive at this point. Simple pimple, huh? These PERT problems are nice because you don't have all the parentheses and plus this and that. Whatever. All right, so let's type it in. So we're going to type in the natural log, and then we're going to, into our parentheses, type 1,000 divided by 15. Close the parentheses. And then you're going to hit divided by 0.07165. Hit enter. And hey, that's not all that unreasonable. That means that for that money to turn into $1 million at that interest rate would take approximately 58.61 years. That's not unreasonable. I mean, it seems like a long time, but if you invest that money when you're 18, then when you're 76, looking for some retirement fundage, then there you go. So that is how all of this works. I'm going to give you a very long assignment today, assignment number 18. The first page is all just the meat and potatoes. I haven't done any word problems on page 1. It's all just P, A, R, and T. All the information is there. You just have to practice the mechanics. And then starting on page 2 is where you'll start to see word problems. And there'll be multiple versions of this assignment. The only thing that'll change as we go from assignment to assignment is that what you see today as the first page will go bye-bye. From now on, after today's assignment, they'll all just be word problems. So you'll get used to that. Good? All right, cool.